Alright, my name is Blaze Banks, and this is my extra credit submission. I took a deep dive into the Bloom filters data structure. So, consider that users are creating an account on your website, and you need to ensure that they have a unique username from all the other users. You don't want new users to experience delays while they're creating an account that could cause them to not want to use your site in the future. As such, you cannot simply check every current account in your database to determine if the username already exists, as that's just far too slow. But precision here is not strictly necessary. You need to ensure that no two users have the same username, but you don't need to ensure that every username can be used, especially if that event is relatively rare. So, the data structure that would be best for this is a Bloom filter. This is invented by Burton Howard Bloom in 1970. He was looking for a way to eliminate unnecessary disk accesses by first checking the membership of the items that he was looking to access. He was also looking to minimize memory usage while still retaining quick checking for whether or not an item exists. This was also previously used in Google Chrome's malicious URL detection. They added all the flagged URLs to a Bloom filter and would first check by that, as it was very quick and wouldn't slow down search times. A slight variation of these can also be seen in nature and is used by fruit flies to detect new odors, which is really cool that there's some biological systems that mimic this data structure. It's also used in spell checkers to see if a word exists in a dictionary really quickly. The structure of a Bloom filter is quite simple. It's just an array of m bits, and the filter has k hash functions that it uses. An empty Bloom filter has all of the bits set to 0. Insertions change some of the bits to 1, and an element is not in the set only if at least one of the k positions that the hash functions output for that element is still set to 0. So unlike many other data structures, Bloom filters don't actually store the element that you insert, they just represent whether or not it exists using the values of its outputs from the hash functions. This makes it a very space-efficient data structure. So Bloom filters are a probabilistic data structure. This means that they can't give you an exact answer to your queries, but instead the Bloom filter can only tell you if an element is definitely not in the set or if it probably is in the set. This is because hash functions can output the same result for different inputs. If all k of an element's related indices have been set to 1 from other inputs, the Bloom filter will say that the element exists even if it hasn't actually been inserted. But there's no way for an element's related indices to be set to 0 after insertion, so there's no chance for a false negative, but false positives are possible. To insert an element into a Bloom filter, you pass it through each of the k hash functions and set all the bits that are outputted from the outputted positions to 1. We'll insert an element e into a Bloom filter where m equals 24 and k equals 3. So we'll input e into these 3 hash functions. We don't necessarily know what they are, we just know that they work for this example. So the 3 hash functions will say output 0, 7, and 18. So we set the indices of the array at 0, 7, and 18 to 1. Now we'll insert some second element f. F goes into the 3 hash functions. The functions output 2, 7, and 16, so we'll set indices 2, 7, and 16 to 1. There actually is a collision here at index 7, but that's actually okay and is part of how the Bloom filter functions. Now we'll insert a third element g, which goes into the 3 hash functions. Functions output 4, 9, and 22, and we set those indices to 1. To check for whether or not an element has been input into the Bloom filter, we have to plug it into all k of the hash functions and then check all of the outputs. If any of them are 0, the element has not been inputted, and if all of the indices are 1, then the element most likely exists. So here, we'll check if some element, we'll call h, is in the set by inputting it into the hash functions. So h goes into the 3 hash functions, and these functions output 9, 14, and 23. So we'll check indices 9, 14, and 23, and the bits at those indices are not all 1. As we can see here, they're 1, 0, and 0. Even though 9 is set to 1, the rest are not, so we return false. As long as one of these is 0, we will say that an element is not in the Bloom filter. Now we'll check for another element we'll call I. We'll say I goes into the 3 hash functions, and these functions output 2, 16, and 22. So we're going to check at index 2, index 16, and index 22, and these are actually all 1. So what this means is even though we never inserted element I, we've still returned true that the element exists in the Bloom filter, which is an example of a false positive result and is one of the largest drawbacks of using a Bloom filter. So for the complexity of a Bloom filter, the time complexity of insertions in membership queries are all based on the number of hash functions k, so they can be considered big O of k. However, k is generally a relatively small number. We'll get into the determining how many hash functions to use later, but this can be considered constant, and such a small enough number that these operations are considered constant time big O of 1. As for the space required, approximately 10 bits per element are needed to have a false positive rate of less than 1%. The math behind that is beyond the scope of this presentation, but that is the result of it. This is a lot less space than storing an object, which generally has multiple strings, integers, vectors, etc. stored within it, and most other data structures will be storing the entire object within them. So looking at the complexity comparison, looking at a Bloom filter and an unordered set and a binary search tree, which can all be used for checking whether or not an item exists. The time complexity for insertion is O of 1 for Bloom filter and unordered set, and big O of log n for the binary search tree. The lookup time is the same as insertion time for all 3 of these data structures. And the space complexity is about 10 bits per element for the Bloom filter, whereas for unordered set and binary search tree, the entire object has to be stored. So some pros for the Bloom filter to consider is that this is very quick for checking membership, and it requires much less space than other data structures. It will also never fill up, even if all of the bits have been set to 1, and insertion will never fail like it might in a hash table. These also scale very well for large data sets. That is, their primary use is for really large sets of information, and they can also never produce false negatives. But there are also some significant drawbacks for this data structure. They can yield false positives, and this false positive rate increases as more insertions are made to the filter. They also rely on the hash functions that you choose for efficient functionality, and that determining which hash functions to use can be somewhat complex, as you need k number of hash functions, and k can change and increase, and you'll need to determine more hash functions to use. It's also impossible to delete an item from a simple Bloom filter, since multiple inputs can hash to the same output, and you wouldn't know which one has been input. So considerations for whether or not a Bloom filter is the correct data structure to use for your application. You have to choose hash functions that distribute uniformly throughout the array, such as murmur hash is a very good one for this. You can't have clumping near the start or the end. That can throw off the false positive rate. Elements can be added but not deleted, so these are not well suited for frequently changing data sets, dynamic data sets. The optimal number of hash functions for a Bloom filter is m divided by n times the natural log of 2. The math behind this, again, is beyond the scope of this presentation, but here m is the size of the array and n is the number of inserted elements. Bloom filters are highly effective and efficient for a very small number of use cases. So membership queries on large, mostly static data sets, where a little bit of error is possible, is where these data structures thrive. But these are really not suitable for cases where exact precision is required. Thank you. Here's the sources.